Hello, everyone. Good morning, good afternoon, and good evening to everyone who's tuned in. On behalf of PioPetro, Arab Oil Gas Academy, and SPE Egypt section, I would like to welcome you to today's session. My name is Shahad Bahjat. I'm a third-year petroleum engineering student at KNU in Kurdistan, Iraq, and I'll be your moderator for today. Before we start, I'd like to remind you to please drop your questions in the Q&A section below. Please keep the chat box professional and ethical, and please submit your quizzes before the deadline. Now, without further ado, please give a warm welcome to Mr. Kirk Harris, who will be giving us a short course that consists of 4 webinars on cement evaluation, the basics, and beyond. Mr. Kirk Harris graduated from Purdue University with a bachelor's degree in civil engineering. He started his career at Halliburton, where he worked as a cementer, operations and research engineer, and technology manager. He is currently the technical advisor for Through Bond LLC, which provides technical support for cementing and bond log interpretation. Prior to his work at Through Bond, Mr. Harris was the global cementing advisor for Occidental Petroleum, Talisman Energy, and Repsol. He has been the regional cementing advisor for Asia Pacific, the North Sea, Europe, Africa, the Permian Basin, and the Gulf of Mexico, and he is currently based in Lafayette, Louisiana. His opening session will be covering the basics of cement bond log tool and a basic interpretation method called the 5 C's. Mr. Harris, thank you so much for coming, and the mic is yours.
Thank you very much. It is a privilege to be speaking to you this morning. Although I understand we're getting some funny connections, so I ask for your patience if my voice disappears for a while. We're getting a bit of an unstable connection. For the second session, I assure you it will be cleaned up and we'll make sure we don't run into this issue. Again, my name is Kirk Harris. We're going to talk about the basics of the CBL as we look at cement evaluation. Next week, we'll look at the ultrasonic log specifically. The third week, we're going to look at more of advanced interpretation. Specifically, when I receive a log, how do I interpret it? I receive about one a day. I receive a few hundred a year of logs that I will interpret, and we'll go through that in week 3. In week 4, we're going to shift and look at the shallower casings and look at shoe tests in week 4 as we wrap up cement evaluation. What I'm about to tell you, you can and cannot both find it in a book. What I'm doing today, I'm teaching you as if I'm an audiobook, but what I'm going to teach you, although it is simple, it is not easy. It's like anything that's a little difficult for us. We may be able to read about skiing on the slopes, but to actually do it is a little more difficult, and I will explain why. Many disciplines, I guess you can read about it. If you trust the author, you can read about it and learn it. Here, you're going to have to practice it. But I will say there are 2 publications. Be in connection with me, I can lead you to these 2 publications and give you more things to read. But one is the API method, or the API best practices for approaching cement sheath evaluation. The other, I've taken a page out of the Schlumberger book. Schlumberger writes very well about bond log interpretation or cement job evaluation. So I would recommend both of those to you. Today, the agenda, we'll talk about the basics of cementing very quickly, and then we'll move to the CBL, cement bond log basics. how to interpret the bond log, and why this tool, this method is controversial. It's kind of funny. I received a bond log about a week ago from South America. In South America, the manager who sent me the log said, "Can you interpret this log for us? And if so, how much will you the log?" So I said, "Well, I can look at it and I can give you my opinion for free. There is no cost for my opinion. But if you want in-depth explanation, a full report, an understanding of everything on the log, then I'm going to charge you a very small amount. Not much, very small amount." And he said, "That sounds great. Let's do it." And then he called me back a day later and said, "We can't do that. My bosses do not like the bond log. The bond log is too difficult to understand." So I will finish about why this bond log is controversial, why some love it, why some hate it, why some think it's a good tool, others think it is confusing. We're going to talk about the bond log and the ultrasonic, both. We'll save the ultrasonic for next week. This is a combination bond log and ultrasonic. Bond log on the left, the colorful map we'll look at next week. We're going to focus on this, the CBL. And as you look at that, I don't know if this is your first webinar on bond logs or if you've attended others, but the bond log is a simple log. 5 curves, easy to understand. To interpret them, we'll look at, is a little more tricky. This is the purpose, this is the reason that we're learning about bond logs. Someday, if you're in upstream oil, you will find yourself gathered around a bond log. This happens to be a school I was teaching a few years ago in Colombia, but you will gather around the log with drilling, with production, with supervisors, with managers, engineers, geologists. Almost every position in the oil field upstream will touch that bond log. As we abandon wells, I look at many bond logs to assure that we have a secure abandonment, a well that has integrity as we abandon the well using the bond log. So I hope that you get the opportunity to be gathered around the bond log and watch the dynamic that occurs, because people will be arguing, people will be talking, it will be noisy, and you may be in a position to be able to help interpret that log, or even to take a leadership role in being the go-to person for your company for bond logs. There's not many out there. I want to be honest. Most of the time, we allow the logging company to interpret the log. If not, it goes to the geologist or the petrophysicist in an oil company. Unfortunately, cementing companies do not interpret very often, and the oil company itself, the drilling team, often allows others to do the interpretation. The cementing basics, very quickly. What we're trying to do when we run a bond log is to determine the success or the quality of the cement job. We're going to pump with a high pressure unit cement down the casing, up and around into the annulus, between the hole and the casing, and we want to seal that annulus with the gray cement. So we'll circulate the hole with fluid. We'll then pump a spacer to help clean up the mud to get a clean hole. We separate the cement from the mud with a plug. We pump the cement. We then separate the cement from our displacing fluid, which is a water or a mud, and we pump it all the way to the bottom of the casing so that inside the casing there is no cement. Outside the casing, we have the cement sealed. At the bottom of the casing, there is a check valve. We call it float equipment to keep the cement from coming back inside the casing. We then wait for the cement to set up and run a bond log. So we mix the cement, beautiful gray cement. Here we're mixing it. It's being mixed on the left side of this tub, being poured over into the right side of the tub, where we'll then let it go to the high pressure pump and pump it down hole. On top of a bottom plug B, through a cementing head, and we're going to pump that cement on top of that plug, then drop the top plug T on top of the cement and displace it with liquid. There we're taking returns, going down the casing, up the annulus. What do we do next? What's the next thing we do? We've pumped the cement through the casing. Hopefully it's made it to the outside of the casing, has been lifted up, covering our zones to cause isolation so that the oil and gas doesn't come up to surface or come up to a previous or another formation, such as a freshwater formation. What do we do next? Part of one of the favorite things I like to do. That's we sit back, we relax, we pour our coffee, and we wait. We wait. While we wait, the cement is setting up. We're then getting ready to run the bond log. We're going to wait 24 to 48 hours for the bond log. At the end of this session today, we're going to talk about one of the disasters or some disasters that have occurred, including Macondo. And for Macondo, we did not run a bond log because if we were going to wait 24 hours, that's $500,000 of waiting time before we can run the bond log. So the bond log costs money, but the waiting costs money as well, as it is on the critical path sometimes. And so sometimes we have to design the cement to set up faster to be able to run a bond log sooner. And at the end, we have a cemented well bore. We have the formation, the cement fluid, which becomes part of the well bore. So let's look at the tool that we're going to run inside of this well bore. And it's kind of interesting because I don't know if you've ever thought about it. Sometimes I think about things in the oil field that probably I shouldn't be thinking about or no one else thinks about. I imagine going down the well. Does anyone ever imagine that? That I'm going to take a trip down the well bore, a couple miles. Can you imagine how quiet it is down there if you're just sitting down there? I've been inside a cave before, only 100 feet into the cave, and it was dark and it was quiet. Well, it's very quiet, and we're going to run a tool down there and start making some noise. And when we run that tool, this is the tool, we're going to make that noise with a transmitter for the bond log that is making an audible sound. The sound that it makes is a clicking sound. Very rapid. And we're listening for that sound 3 feet away and 5 feet away. And we're listening for how loud that sound is. And when does those sounds arrive? And after we hear the first sound, what other sounds are we hearing? Let me take a look back here. This is inside the shop of a logging company. And I've kind of hidden what I want to show you here, but behind this screen that you see is a test cell where we will run that tool that we just saw inside the test cell, and we will measure. Here we go. And we will measure how loud the tool is in there, and different companies do it differently. Some companies will run it in this chamber and they will just make sure that the tool is working, that it functions. Others will calibrate this tool and they will listen to see how loud it is in pipe that is not cemented. And we get various free pipe amplitudes when we sound that tool off. So here's our tool going into the well bore. We send the sound wave out. It goes in all directions. We're looking at one specific pathway. In this case, showing the arrows going down the casing, which quite often is the fastest route to the receivers because sound travels through steel faster than liquids or the cement. The problem with the bond log tool, we go down the well, it's very quiet. We send out sound waves and we start listening for echoes. If we're in the open hole, no casing, no cement, open hole sonic logs, the sound goes out, it reflects off of the boundary, which is the formation, and comes back. We get a nice clean sound wave coming back. When we put casing into the well bore, as the sound wave goes and it hits the casing, whatever's on the other side, if it's a solid, the sound wave passes through. But if it's liquid or it's poorly bonded, then it reflects back and starts to echo. So when you put casing in the well, it's like going into a tunnel that is made of a big piece of steel. You start shouting, you start getting echoes. And these echoes start reflecting and make the bond log a little confusing. But we're going to use Snell's law to determine if we have cement. The more alike these boundaries are, the more the sound will travel through. The more different they are, the sounds will reflect. So if I have my casing is in air, a big difference between the air and the glass, I get a very loud ring because all of my energy is staying in the glass or in the casing. If I cement the glass, then the ring and the resonance of the ring goes away, because I'm now supporting the casing with something that's like the glass, a solid. So when I have loud ring or high amplitude or loud sounds coming down the casing, I have no cement. If it's a small sound, all of my energy has gone out. The small sound coming down the casing means I do have cement. So when I have cement, I send that sound wave out. It goes through the casing, through the cement, reflects off of the formation. Again, the first part of the sound wave that I sent out, that's going to arrive at the 3-foot receiver first. The first part of that wave is traveling through the casing. It's moving fast, so it arrives first. The second is going through the cement and formation. And the third part of the curve is coming down alongside the tool inside the logging fluid. And then we get our bond log display. Simple, only 5 curves on this log. You only have to know 5. But if it's the first time you've seen the log, it looks a little confusing. It doesn't necessarily show me a picture. Here are the curves that are on the bond log display. The green curve is the gamma ray. Nothing to do with the bond log. It's just telling us the natural radiation of the wellbore, separating sands from shales or limestones from shales. The middle line there, the dark line, is the transit time. The transit time. It is telling us from when I click, when I hit the transmitter, to when I receive the signal. This transmitter is being fed electricity through electric wire line. When the electricity hits the transducer, it causes the transducer to contract and sends out a pulse, 20 kilohertz in frequency, a sound that you can hear if you have good ears. And when it goes out, the time it takes to get to the 3-foot receiver is the transit time. The casing collar locator is the hashed line. It tells us where the pipes are jointed together. It's that extra massive steel. It's basically a magnet telling us where the large steel volume is at the joints. The middle curve, and I will warn you, at Therabond, we are very hesitant to spend too much time looking at the amplitude curve. This is basically how loud is that sound, that first sound we hear at the 3-foot receiver coming through the casing. How loud is that? And then we have the variable density log to the right. That's the 5th curve. That is the history of the sound wave. Time versus depth to when I receive it. The amplitude. The amplitude is the height or loudness of that first wave that arrives. In this case, it's fairly small. The big peaks coming later, those are big sounds reflecting off of the formation. But that first area is coming through the casing. That first peak is the amplitude. I will repeat, at Therabond, we do not use amplitude specifically to interpret the log. We will read the log for the CBL. And we will be looking at several things on the variable density log that we will observe when we interpret the log. But we take the variable density log. I'll show you how we make it. We cut it in half. It's like being in the ocean at sea level and watching one wave go by. The height of that wave is the amplitude. We take that. We're going to cut that wave in half, rise out of the ocean, and look down on that wave. And when we do, it would look like this. And now we'll do that as we go along the beach of the waves coming in. We will mark the peaks of all of those waves, and we will connect them to create the VDL. Again, it's like flying over the ocean now, looking up and down the beach, that's our depth, and looking at the first arrival that's hitting the receiver, a history of the waves that are about to come in and be picked up on that receiver. So every time you fly over the beach, you're looking at a VDL. I see VDLs everywhere. I see them when I look on the beach. I see them in the clouds. I see them on the lake. When I throw a rock in the lake, I see the waves coming in. You see beautiful VDLs all over the place. So be watching for those VDLs. And that's what we look at, time versus depth. When we look at the VDL, we'll see it to the far right, 5 curves. You get the gamma, the dotted line in the middle is the transit time, foot receiver. The hashed line is the casing collar locator. The middle area, we have 2 curves. They're the same curve, different scales. This is measured in electrical energy. It's the amplitude. This particular log, and it changes from log to log. This particular log from 0 to 100 millivolts. And then we have another curve, the amplified amplitude, 0 to 10 millivolts. And then we have the VDL, the variable density log. And that's where we'll have our focus when we interpret our bond log. When we look at that, the first part of the wave, the first wave hitting the beach, is the fastest sound and that fastest path, and that fastest path is traveling down the casing. In this area, we look for straight lines because it would be a lot of energy, and since it's coming down the casing is homogeneous. Always, if our tool is centralized, we get the same fluid, the same casing, the same fluid. The wave should arrive at the same time up and down the well, and we'll see straight lines. In this case, it's a perfectly cemented well, so the lines disappear. There are no straight lines. And a basic rule, if you see straight lines, that's bad. Straight lines are energy coming down the casing. Straight lines are the same as a loud casing ring. When you see no lines, the energy is so small we can barely pick it up because it's very quiet sound. The middle part of the curve comes through the formation, big formation signals. And then the last part, we'll see effects coming through the fluid. All of these waves coming in, and the construction and destruction of these waves as they come in show up in the VDL. Very quickly, you're going to see some colored maps today, and those are from radial bond logs, where we have the regular cement bond log, 5 curves. We add to that a cement map. That's based on 8 separate receivers, either at the 2-foot or 3-foot interval. By the way, the VDL comes from the 5-foot receiver that we saw earlier. The cement map will come from radial receivers listening on each side of the casing at the 2 or 3-foot interval. When we come to look at the bond log, the key thing, and I see people who have talent at this, and I see people who do not, and that is we have to learn to observe. To observe, you need to use your eyes. You need to quiet the rest of your senses. I can observe and taste coffee at the same time, so I think that's okay. But I actually usually taste the coffee first and then observe. I want you to see the eyes. If you're talking, it's hard to observe. If you're in a hurry, it's hard to observe. If you don't know what to observe, it's hard to observe. So I want to take you through the things that we will observe. There are 4 main things we'll observe when we look at the bond log immediately. The first thing we will observe is casing ring. Casing ring shows up on the VDL as straight lines. Do you see any straight lines on the VDL, the curve on the far right? A lot of them. Matter of fact, if that VDL was this glass, not only do you hear a first ring, you hear it resonating, big ring all the way throughout. There is no cement. So we observe the casing ring. Look at these logs. The log on the left, do you see straight lines? Do you see casing ring? Especially first arrival casing ring. We do. We also see the big chevron patterns at the collars. How about on the right? By the way, the log on the left has no cement in it. The log on the right, do you see straight lines? They're not as strong, but they're there. And the collars are not ringing as loudly, but you can see chevron patterns here. But here, they're not as strong. Here you see the strong chevron patterns. Do you see straight lines here? When you see straight lines, first arrival, that's bad. At least it's going to require some interpretation. If you see no straight lines, then you don't worry about it, or many don't. Maybe we should sometimes, but I never receive logs that have no straight lines. They don't send those to me. I only see the ones with straight lines that cause bottom. They go away. The next thing we will look for are formation signals. First of all, do you see any straight lines in this log? You see some to the far right. Those are fluid arrivals. But to the left, here in the VDL, all of the straight lines disappear. That's good. But we want to make sure we're connected to the formation, and they will show up as these big, crooked, squiggly lines. So very basically, straight lines are bad, squiggly lines are good. We're connected to the formation, we're reflecting off of the formation. We must be connected by cement. Do you see any formation signals here? Do you see any straight lines here? No straight lines, but look at all of the crooked lines or the bending lines. Those are all strong formation signals. It's a perfect cement job. What about here? Straight lines, do you see any? Just look at the VDL. Do you see any chevron patterns at the collars? I do see straight lines. I do see chevron patterns. But do you see any formation signals? Look at them, strong formation signals. We must be connected to the formation. That is a very good sign. The third thing we'll observe, the first we look for casing rings, second formation signals. Casing ring is straight lines. Formation signals are crooked lines. Look at this log. Do you see straight lines? A little bit in the bottom. Do you see formation signals? I do. Strong crooked lines that follow the straight lines. If we can apply pressure to the casing, which we do here, we place 1,000 psi inside the casing, it expands the casing, it strengthens the bond, and the straight lines go away. So if we do have a pressure pass, then it can give us some good information. Here's an example where we ran a pressure pass, and just look at the colored map for a second. Again, this is a radio log, not an ultrasonic. We'll look at ultrasonics next week. And you don't see much change, do you? We tighten the bond on the one on the left. It changes a little bit, but there's not much change of the colored map on the right with no pressure. So it tells us adding the pressure did not help. We may have a big problem here, more than just a bond. And the final observation I will look at, I get the log, I look for straight lines, casing ring. I look for crooked lines, formation signals. I see if there's a pressure pass, and I observe the pressure pass if anything has changed. And then I look for top of cement. Where does it go from no straight lines to very big straight lines? And I try to find the top of cement. I will use that top of cement so I can compare and analyze the rest of the log. Results. As a matter of fact, we will talk in just a moment, but when you cement an oil and gas well, for the most part, these are your only 4 options. These are the only 4 things that can happen when you interpret a log. They happen in different ways. They happen in different mechanisms cause it, but you either have no cement, bonded cement, we might call that a microannulus, or the cement has channels in it, either mud channels or gas channels, or it's a good cement job, perfectly tightly sealed. Let's look at what each of those looks like. This one's pretty evident. A lot of straight lines. If you look at the CCL, and again, you'll have these charts. Here's our CCL, our casing collar locator, transit time dotted in here. Here we have our gamma ray. We actually are showing here 2 transit times. It may be the 3 and 5 foot receiver. Here's our amplitude. Here's our VDL, and this is our cement map. Straight lines, no cement, big chevron patterns. This is free pipe, what it will look like. Straight lines, chevron patterns, strong chevron patterns. Here's a microannulus, poorly bonded. We have straight lines. They may not be as strong, or they might, but straight lines, but the collars are dampened. You see a change in the collar. I look at that a lot on the VDL. And we have formation signals. You see the crooked lines. Here's what a channel might look like. The unfortunate thing is that a channel often looks like debonded cement. And on the 3rd week, we'll talk about some more advanced techniques to determine the difference between a channel and poor bonding. But once again, you get straight lines with the channel. We get the collars. They're dampened somewhat, but they're pretty strong. And you get formation signals where it's attached. On the cement map, because a CBL cannot detect channels on its own, not clearly, but we see the channel coming from this water zone that we know is flowing. This is a big channel. When we look at the ultrasonics, we're able to see smaller channels. And then we have perfect cement. That's what it looks like. No straight lines. Matter of fact, it looks pretty much like the open hosonic log. Everything's so tightly bonded, so solid, that we just reflect the formation back. And that's what we want to see. Look at that beautiful cement job. We can get these kind of cement jobs everywhere. We can. In the most difficult of circumstances, we can get a great cement job. But we have to be ready to do some serious cementing. Sometimes we have to be aggressive. We have to understand the entire wellbore, but we can get these kind of results. What about this one? Do you like this one? Why do you not like it? I mean, I don't like it. Because we see straight lines. Many will say, I don't like it because the amplitude here is 72 millivolts, which happens to be the free pipe amplitude for 5.5-inch casing. So the amplitude says I have free pipe. The straight lines say I have free pipe. The collars start to get dampened, and then we see what appears to be formation signals. Or are they? What are those squiggly lines? Notice if we observe and we take our coffee and we relax and just observe, if we took our time, we probably could make 1,000 observations about the VDL alone. Just look at the VDL. Make some observations in your own mind. What do you see? Simple observation. Do you notice that the first line is narrow, the second line is bigger, the third line's narrow? Do you notice that? That's just an observation. Do you notice the squiggly lines to the right? Don't tell me what they are, just do you notice them? They're squiggly. Sometimes when we start to observe, we start to interpret instead of observe, to just observe. Here's another observation. How many straight lines do you see before the squiggly lines? And does it change? Count them. 1, 2, 3, 4, 5, 6, 7. There are 7 straight lines before the squigglies start. And notice, it all happens right at the same point. This is an indication, and it's something we observe. These are fluid arrivals coming down the casing, distorting the straight lines. These formations, although we may be seeing some effect if the casing comes over to the side and touches the formation, what we're seeing here are fluid arrivals. This happens to be free pipe, no cement. So these are the things that we will observe. Now that we have kind of the basics, what is the method? How do we interpret bond logs? We call it the 5 C's. Some of you may have joined or have seen our 5 C's before. You will know what we're getting ready to look at. We're going to construct the well first. What I mean is, although I love the bond log, I'm not going to trust the bond log. I'm going to trust the cementing operation. In other words, if I pump cement and cement came all the way to surface and I saw the cement at surface and the bond log says there is no cement in the well, I'm going to doubt the bond log. I'm going to trust the well construction first and foremost. In other words, I'm going to allow the well bore to interpret the log before the log interprets the well bore. And if you're not thinking about the well bore, if you're thinking just about the log, you will misinterpret the log. So I'm going to kind of build the well as best I can. I'm then going to look up and down and compare sections of that log. When I do that, I've already allowed the well bore to interpret the log. Now I'm going to look up and down, and I'm going to let the log interpret the log. I'm not going to look for absolute numbers as much as a comparison of what parts of the log look like. And I do that by just looking up and down. Now I have to have my coffee in hand to keep me relaxed. I promise you, it's the best part of my day, having coffee and just looking at the log and relaxing but knowing what to look for makes it a lot easier and a lot more enjoyable. The third step is to correlate. Once I look up and down at points of change, I look side to side. Wonder what's happening here. I look to see if it correlates to the wellbore. So I let the wellbore interpret the log. I look up and down and let the log interpret the log. And then I look side to side and let the log interpret the wellbore. That's the process we use. In week 3, we'll look at this part much more. I consider all of the things that the wellbore is doing that's trying to confuse the log. And the wellbore will try to do 35 things. We're up to 35 things we've noticed, and I'll show you a few of those. And then we conclude. So I construct the well, I compare sections of the log, I correlate side to side, I consider what could be going on with the wellbore, and then I conclude. And it's time to interpret. Now here's the problem. You are attending this session, and you will have heard for maybe the 4th or 5th time, I do not use the amplitude to interpret. The problem is when you gather around this log, you're going to find that it is noisy. People are talking. Most of the time, and I've done this many, many times, working in-house at many operators, but working for Oxy and Talisman and Repsol, when I walk into the room, and they would know, hey, Kirk is coming up. He is focused on bond logs. We respect his opinion. And so let's let Kirk look at this. So they call me and I come up to the business unit or fly up to the location. And I walk into the room and it's noisy. Someone might say, hey, hello, Kirk, welcome. Come on over here. And I say, well, what do we have here? And they say, I'm glad you showed up, but we've already interpreted the log. We got the answer. And they got the answer by looking at the amplitude. And so I try to quiet them down because they take the log, and here it is, and they say, let's interpret this log. I said, okay, let me get my coffee. Well, Kirk, we don't have time for coffee. We've already interpreted it. All we did was we drew a line on the amplitude curve. And you can see at the bottom, it's good. Everything's to the left for the most part. But at the top, it's bad. Everything to the right. And so we finished interpreting. And I say, well, wait a second. Let's have some coffee first. Thank you. Now we can interpret. And I do the interpretation by asking 4 questions. This is how I start. I ask the 4 questions, first of all, to quiet the room, because someone's already got the interpretation, and that interpretation is wrong. And so I have to get them back to the base of, hey, where was the cement supposed to be, by the way? And then suddenly someone says, oh, well, I don't know. Has anyone looked at that? I guess we are talking about cement. Was there a lead and tail? Did we have losses or flows? Maybe we put all the cement in there and it all flowed out. I don't know. What do we know about the construction of this well? Do we have a weak casing to cement bond? Someone will say, well, what has that got to do with the problem? And I will say, it's everything. The bond for a bond log interpreter is everything. 80% of all logs are affected by shear bond. Just want to take a quick diversion here. I don't know if any of you have climbed poles recently. When you get to my age, your pole climbing days are long gone. They're over. I tried to climb a pole about 10 years ago, and I jumped onto the pole, but all I could do was just hang on for dear life. And so if you're young and you like to climb poles, just do it now. Later, it's not going to be pretty. When you're hanging on that pole, your weight pulling you down divided by the area that your hands are holding on to, that's shear bond. It is the force applied to push casing out of the cement, that cement surrounding cemented. Shear bond, very important. So I asked, do we have a weak casing to cement bond? Maybe it's low shear bond. And then the fourth question, and if you don't know a geologist, you need to get to know one because the formations have a huge effect in bond logs. I asked which formation is causing the problem. So first we construct the well bore. I want to know about the very simple terms. I want to know where is lead cement and where is tail cement. This looks like free pipe. It was interpreted by a major logging company on location as free pipe when it actually was the lead cement. And we need to be able to interpret that. We look at the cement, we look at the casing, we look at the formations when we construct the well. Sometimes you have a lot of data, sometimes you don't. The more data you have about the cement job, the better the interpretation will be. Then we compare log sections. You can look and see the difference between the top and the bottom of this log. And I put there's my lead cement. That was interpreted as no cement, but it is lead cement. And then I take that lead cement and I compare it to what is free pipe. I'm comparing, and you can see the difference between my thumbprint on that VDL and the free pipe interval above. What is below was not free pipe. Although look at the amplitude. The amplitude is the same. And then I correlate at changes. Straight lines bad, crooked lines good, and I get good, bad, good. When I correlate, I just draw at the points of change. I draw a line over and correlate to the bottom and to the top. And now your job as an interpreter, as a detective into this log, is to determine why did it go from good to bad. There's got to be a reason. Your job as an interpreter is to do that. Step 4 is to consider the key factors, things we're doing on location. Here we're running a casing, we're centralizer. What things are we doing on location that will affect the bond log? I'll give you a few examples. There are 35, and we'll dive into those in week 3. The first is new casing. Some new casings, this casing from Argentina that was shipped and run in the Middle East, showing free pipe amplitude, a lot of straight lines, that's bad. Some crooked lines, that's good. But it's showing a bad cement job, but it's brand new casing causing the problem. We sandblast that casing, we take off all the pretty paint and shine, and you see the straight lines in those sandblasted joints disappear. Considering the key factors, centralization. You can look at log A of log and see the line in that colorful map. It's because that particular casing was not centralized. So we like to look for where is the casing centralized. Lightweight cements. Look at the straight lines in the upper portion of this log and watch those straight lines disappear. Both have crooked lines, but the upper one is being hidden by the straight lines. The shear bond of the cement in the upper is only 50 psi. It's 200 psi below. We find that we need about 150 150 psi of shear bond to get those lines to disappear. So lightweight cements we must consider. Here's our lightweight cement. In 24 hours, we only get 260 psi. That's so low, it doesn't want to log very well. It can provide isolation, but it doesn't log. Another consideration, pressure test. When we cement the well and before we test the casing, look at all of the crooked lines. Once again, looking at the bond log, we have the gamma. We have the transit time you can barely see, casing collar locator, low amplitudes for the most 1000 psi, and we break the bonds. So pressure testing we have to consider when we interpret a bond log. I see this on so many logs. We cement the well, we wait 48 hours, we pressure test the casing, we break the bonds, we run the bond log, and we are confused. A final one here is cement shrinkage. When you have cement shrinkage, sometimes you also have gas bubbling. The cement shrinks away from the casing and the bubbles come up. That's a big problem. So we put expansion additive. We sandblast the casing so the cement will lock into the grooves, and we add an expansion additive which tightens the bond. That the cement expands and presses against that casing. Not only do the straight lines disappear, but we find the gas percolating also disappears. And finally, we conclude, not only do we have zonal isolation, not only good or bad, but why or why not? Why do we have zonal isolation? What do we see on the log? Or why not? What's going on? That's what we want to do in interpretation. And when it comes to cementing, you only get 5 choices. There are 2 good choices. We either have good cement, shale. We either have cement providing isolation, or we have a geologic barrier that has come in and provided isolation. Do we have isolation or not? I don't know, because we may have a weak bond, and that weak bond may be enough to have isolation, or especially with gas wells, it does not. And then when it comes to no cement, you only have 2 choices. It's either no cement at all, or it is a channeling issue. Cross flow wiping out the cement would be part of a channeling issue. So these are the choices we get in concluding. So we interpret the log, we construct the well, we compare sections, we correlate side to side. We consider all of the things that could be happening, maybe a pressure test, maybe new casing, maybe a lightweight cement. Then we conclude, and we don't conclude by saying good or bad, we say it is bad because of a mud channel, and here's what's going on. So it gets more in depth. You will understand as we begin to close here, you will understand the more you're around bond logs, how controversial they are. They're controversial and hides some things. And to look at the raw data, it can lead you one way or the other and can be wrong. Here are the 3 reasons why they're a bit controversial. They are simple, 5 curves. The gamma, the transit time, the casing collar locator, the amplitude. They are simple, but they're not easy to read. As soon as you put casing in and have case toe, those straight lines start hiding some of the data. We also have logging versus drilling. And here is where logging is going to look at the logging data. In this case, they drilled a well, and what you see to the right is what we're going to look at next week, and that's the ultrasonic. And what we have here is a log that showed up green. What does green mean? For the ultrasonic tool, the USIT, Schlumberger's tool, green means microbonded. It means it's kind of like a microannulus. There isn't much there, but something's there. The bonding is low, but it's quite variable, so something is there, and they color it green. And so they ran this log, and they colored it green. And we asked, is there cement there? And they said, we're not sure, but let's send it out to be processed. And they sent it to be processed, and they said there is cement there. Well, we said, well, if there's cement there, what happened here? Here's the bond log for it that we ran 3 months earlier when we knew all of our cement was pumped out the bottom of the well, and there is no cement in here. Free pipe amplitude, this is the one we just looked at with those fluid arrivals on the right. So logging said we had cement. Drilling said we don't have cement. And drilling said the reason I know we don't have cement because we didn't pump any cement in this part of the well. That's why we construct the well. Often logging doesn't have that data when they're running the log. They don't know the history of the well. And so it shows you how important it is to construct that well. Another reason it's controversial is because bond logs cost money. Now, this happens to be an excerpt of the flow chart of Macondo on the Deepwater Horizon. They did not run a bond log. I'm sorry. They didn't run a bond log, but a bond log was in the flow chart. Here it is, way out here. If they had a disaster of sorts in the cement job, if all the cement had gone away, they felt, or if they could not easily determine where the cement might be, they were going to run a bond log. So since the job appeared to be okay, they didn't run a bond log. In the flow chart, they were doing everything they could, sitting it way out here, to not run a bond log. Here's the decision. Did I have losses while cementing? No, let's get on with it. No bond log. If that so, let's not run the bond log. Some people say running the bond log would have cost $125,000. That would have been the bond log alone. It would have cost another $500,000 of time as we waited on the cement to set. Without getting into Macondo too much, the reason it probably failed and the reason this disaster occurred, and I was on the outside of Macondo looking in, very involved because I had worked in-house at BP. I had worked for Halliburton in the Gulf of Mexico, mentoring engineers. And I was working throughout afterwards with people involved with Macondo. I was actually in-house when we were putting the cement unit on the Deepwater Horizon. Very important, very tragic, but it was going to cost a lot of bond log. Had we run the bond log, I think the reason there was failure is that the cement never set, at least not before we started flowing the well. Had we waited on the bond log, that amount of time to run the bond log, I think we would not have had that disaster. We don't know, but I think the cement would have been allowed to set. So let's start looking at closing the session with interpreting a log. And I want to show you the importance of the bond log and how we would interpret it. If you've attended any of the sessions before on basic logs, you may have seen a log like this. How do we interpret it? What's the first thing we do when the log's set before us? I actually just received a fresh cup of coffee. So when you think about the 5 C's, never forget the 6th C. Keeps us relaxed, reminds us we're going to observe and follow a procedure. For me, this is not just theory. I interpret logs every day, and I use the C's. I always have the 6th C, coffee, with me, but I use the 5 C's every day. This is not theory. It's simple, but it sets in motion the way we should interpret logs. You will want to just go in and say, it's bad cement. There's a middle section in here that's bad cement. I know that. I know at least it looks bad, but is it really bad? More importantly, why? You have to understand the whys. And I'm going to show you a good reason for that as we close out today. What's the first thing we do interpreting a log? Already got the coffee. We're going to construct the well. For the purposes of this interpretation, I go and I ask the questions. Where was the cement supposed to be? In this well, it's supposed to be way up the well. This is just a short section at the bottom of the well. Is there a lead and a tail? Yes, there is a lead and a tail, but the lead should be way up the well. This should all be very strong tail cement. Okay. I then ask about things like, did I have losses or flows? I asked the drilling engineer, he said, no losses, no flows. Perfect cement job. Like Macondo, quote, a perfect cement job. Okay, maybe I don't even need to run a bond log if it was a perfect cement job. But we ran a bond log, and I'm glad we did, because we find a section in this casing that doesn't look good. Let me correlate. First, I compare. I look up and down. Let me go back to my construction. My third question is, maybe there's a bonding issue. My first thought, if there is a bonding issue, I've got good bond below, good bond above. It's just poor bonding in an area. Maybe it's new casing. It's not a pressure test, or that would have broken all of the bond. What could it be? Maybe 3 joints of casing are new. Maybe there's something with the casing. Maybe, I don't know. And I ask that question. I also ask about formations. But then I compare and we look at it. I compare these 3 sections looking up and down, and at the point of change, I need to correlate. Why does it go from good to bad? I cannot just say good and bad. I have to explain what's going on as an interpreter. A logging engineer might say, hey, look, it's bad. I say there's not much cement there. And I would say, why? He said, that's not my job. It's not my job to tell you why. I'm just running the log and telling you what the log is saying. I want to know what the well bore is saying, not necessarily just what the log is saying. So I'm going to correlate back to the well bore. And I happen to correlate right to this point. You see the gamma spike? That's our formation. The casing collars are our casing. The cement is all one cement, so that shouldn't change. But I change near a collar, but I change right at the gamma. There it is. When you start correlating, the puzzle starts to be solved. Next week, we're going to look at this log. This log is an ultrasonic log, and we'll look at this in depth. But look at this. I'm considering things, and one of the things I always consider, maybe it's poor bonding. Maybe there are joints of casing that aren't bonding as well. But when I look at this, I can see that the occurrence is not happening at a collar, it's happening at the gamma. I then go to my geologist and say, what is that gamma? Looks like a shale. My geologist says that is not a shale. That's something called a hot dolomite. I find out that the geologist in this infill drilling program knows more about the well than our drilling group does, what we're drilling through. They know the formations, they know why we're doing what we're doing. So I attach myself to a geologist and he says, this spike is a hot dolomite. As a matter of fact, it's overpressured dolomite. And we determine through our interpretation, and every interpretation is just an interpretation. It may be right, it may be wrong, but we determine that this hot dolomite is probably doing something that often occurs. It is cross-flowing into a normally pressured fractured dolomite, and I've wiped my cement out of the picture. And this is important because this well is an injection well. I need cement across this to direct my injection into a new zone that I can flood the oil out of the wellbore. It's critical. And all of my cement is gone. Guess what? If I hadn't run a bond log, I wouldn't know that. I would inject my CO2 and get no increased oil production. If I didn't run a bond log because I had full returns and the job was perfect, I never would have saw this. So what did we do? We perforated at the bottom of the bad and at the top of the bad, and we were able to circulate and re-cement this well. So the bond log not only told us we had a bad job, it showed us the place we needed to fix. And we fixed this well. But it didn't only do that, it also allowed us in the next 20 wells that were going to be drilled in this field, it allowed us to cement them correctly. You see well 2, we put a packer in between that flow zone, and we were able to get a perfect cement job. Look at the VDL on well 2. No straight lines. Beautiful. We did the same thing on well 3. We then allowed that pressure to normalize and we cemented the rest of the wells without a packer successfully. So the bond log not only told us that the perfect cement job was not perfect, it told us how to fix it, and it told us how to cement wells in the future. This tool is extremely useful, the bond log is. Would like to close with a few simple things in our summary. First of all, cement logs are simple. We got the gamma, transit time, casing collar locator. Those are on one side. We got the amplitude in the middle. And it's not that I don't like amplitude, but we cannot draw a straight line and say that interpreting is just left and right of a straight line. Amplitudes will fool you mainly because of the poor bonding that can occur for a number of reasons, and we still have isolation. As an example, every lightweight cement is going to fail the straight line test, the amplitude test. We use the VDL, not the amplitude. But cement logs are simple, but good interpreters must practice. You must practice observation. You must understand the logging tools. I think if you understand the logging tools too much, you'll trust them too much, but you have to understand the logging tools, but you have to know cementing. You have to know the well bore. You better have a geologist nearby. The geologist is usually the go-to person because they work with logs and they know the formations. But you must practice. The things we talked about today, you will forget in about 2 or 3 days if you don't get in front of a log and practice. Finally, bond logs are very useful. They're going to help us to fix wells, help us to cement better, help us to understand where production is coming from. If our well bore is the best it can be, they're going to help us abandon wells and make sure that we have them properly sealed. So be dedicated to your work. Don't give up on the bond log. Don't think that you have to be confused. The more you work with the bond log, the better it will be. So be dedicated to that work. With that, I would like to close, and I would like to hand it back over to our moderator for any questions or comments that you might have. Thank you.
Thank you, Mr. Harris, for a very informative webinar. I'm sure the audience benefited greatly from it. In the meantime, I've collected a few questions for a quick Q&A section. So the first question is, after cementing operation, is it advisable to continue drilling if we have losses when flushing or circulating?
Yes, could you repeat the question? It was after drilling the wellbore?
After cementing operation, is it advisable to continue drilling if we have losses when flushing or circulating?
Okay. I'll answer that in two questions because I'm not sure I understand the exact question. But I'm working with some logs right now to where when we're drilling the well, we're circulating the well without losses. But when we start to circulate before cementing and we have losses, we've questioned, do we cement or do we try to cure losses before we cement? And all I can say is if you have losses and you're not sure where the losses are and you cement, I've got many logs before me. They are the worst cement jobs you can have, having the losses. Now, if the question is, we've cemented the well and everything is fine, and now I drill the next whole section and I have losses, should I stop or should I drill blind? It's drilling blind is we drill ahead with losses. In that case, it's dependent upon each well bore, but we're, for the most part, always trying to heal and seal the losses so we can have full circulation. If we don't, for sure, somewhere along the line, we have a well bore that has no integrity. So I answered that in a couple ways. I hope that the answer was somewhere in that.
Yeah, the second question is, why channels have the same characteristics as bad cement bond on the cement logs? What is the basic idea that makes these two situations alike on the log?
Yeah, it's a very good question. If you have a channel, and let's imagine it's the worst possible channel, half of your well bore, half is cemented. The other half has no cement. So half of the well is perfect, half of the well is not perfect. In that situation, of course, it's a very bad thing because all of your fluids can flow up one side of the well. When you run the bond log says, I'm getting formation signals from the half that is cemented, but I'm getting, those are the crooked lines, but I'm getting straight lines from the half that is not cemented. So the log looks like straight lines and crooked lines. That is a classic channel. But when I have poor bonding, I'm fully surrounded, but I'm not gripping the casing tightly. This glass that I ring, if I'm not gripping it enough to stop the ring. So what do I get? I get the same straight lines, but I'm connected enough in places where I get the formation signals. In both cases, they're straight lines and they're formation signals. The channel is bad. The weak bonding may or may not be bad. Often it is not bad. So I get the same result, straight lines, crooked lines, with two different scenarios. And a talent in interpretation is looking at enough, knowing your field well enough to know the difference between the two.
Great. Thank you for
Good
answering, Mr.
question.
Moore. Yes. We have a couple more questions. Why the amplitude was the same in the example where VDL of lead cement was compared to another VDL which represented a free pipe? What is the basic idea about the amplitude being the same where the two mentioned situations were actually different?
Yes. Once again, especially new casing and lightweight cements, the sound wave, all it knows, it goes out, and what's directly next to the casing will determine where that sound wave goes. And if it is not tightly bonded to the casing, that sound wave says, I'm going to reflect and stay inside the casing, and I'm going to send all of my energy down the casing. Even though cement is present, if it's not squeezing the glass, if it's just barely touching the glass, then all of the energy goes down the casing. There are many other scenarios where the energy will not go out the casing, it will come down. Here's another example. If the cement is so thin that it provides no mass to grip the casing, just because cement is there, it will not dampen or attenuate or carry out the sound wave. It will travel down as if it's free pipe. So in the case I showed, it is a weak cement. Many places around the world allow you to run cement that barely sets up. So it doesn't grip the casing. It has no shear bond. And you must have strong shear bond to carry that sound wave out. I see it more often than you can imagine. Lightweight cements and new casing or pressure tested casing, although cement is there, the sound wave is not fully connected and will travel down the casing just as if it was free pipe. So the case, I showed 2 or 3 cases of free pipe amplitude that was fully cemented. That's part of the problem, just running the bond log, and part of the problem of the confusion of the bond log. That's why we must construct the well and observe closely the VDL. But another good question.
Yeah. Another question is, according to your experience, can this process of interpretation be automated using machine learning and AI? If not, why?
Yes, it can be, and I some time ago I thought maybe I'm the only one thinking about this. Very good how to make your eyes, and I will show you next week. Next week I will show you, as we look at the log, where your eyes should go, what they should look for. And so I thought I was the only one thinking, if I could have a computer program for my eyes to see, we can automate this. I believe we can, but you're going to need a few little secrets on how to do that. So if there's any wizards out there with AI or computers, I'm talking to some people, I think we can automate it. And so, yes, I do. I think there's a few secrets about how it can successfully automate it, but I do believe we can.
Yeah, thank you for answering, Mr. Harris. Thank you again for dedicating some time of your shortly busy schedule to give this webinar and course in general. Thank you, attendees, for tuning in from all around the world. Please stay safe, wear a mask, and have a great day.
Thank you. It's been my privilege. Thank you very much for attending.